Hello friends, this video on structure of atom part 21 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 20. Now let's study the line spectra of hydrogen. So line spectra, let's study the emission spectra. So when the electrical discharge is passed through a gaseous hydrogen, the hydrogen molecule dissociate and the excited hydrogen produce these radiations of discrete frequencies. If you see, only this particular guy is visible, black Balmer. Apart from these are not visible. They are not visible. Only these are visible, right? And all these spectrums, right? Balmer, Lyman, Paschen. I'll show you. They are named after their discoverer. People who discovered, they named it after themselves only. We'll study all this, but the way to do is you just take a hydrogen gas and just pass it through electric, and then they get excited, and when they come down, when to the example these electrons, once they are excited, right, when they want to come down to their natural state, the low energy state, they emit spectrum of photons. And please note here once again that Balmer is the only visible radiation, and that makes sense, right? Since Balmer is the only visible radiation, that was the first to be formed. So let's study the Balmer. Balmer was a scientist in 1885. With the experimental observation, he observed that if the spectral lines are expressed in terms of wavelength, then the visible line of hydrogen spectrum obey the formula. This is the formula where my wave number is r into 1 by n square minus 1 by 2 square. This is for the visible thing, because for visible I know that my final is 2. I'll show you what. So you have, this is second orbital. You come from any other orbital, and you will see a Balmer thing, because that is the visible thing. So in the Balmer thing, we'll take in the next few slides that there is something called, when the electron jump, there is something called initial and final. For Balmer, the final is always 2, because it always comes to the second orbit, correct? And it obeys the formula. Wave number is 1 by lambda, that is nothing but r into 1 minus 1 by n square minus 1 by 2 square. So this is something which always obeys, right? So the series of lines described by this formula is called Balmer series, and they are the only lines which appear, which are visible. And please note, this formula is derived empirically using experiments data available at that point of time. So he did a lot of experiments, and with that he found this formula. Then came the Rydberg. He noted that he gave a general formula actually, where all series of hydrogen spectrum could be described. So in the Balmer series, if you see, only n is equal to 2, where the destination, the orbit is 2, was described. This Rydberg gave a general formula where all the spectrum could be described. And for this formula, wave number is nothing but 1 by lambda, that is nothing but r into 1 by n square minus 1 by n2 square, where n1 is my source. Sorry, this is my target and my source. Yeah, this is my target here, and this is my source here, right? And if you see here, the value of r is the same thing which here used. It's called Rydberg constant for hydrogen. And this, please note, this is value is true only for hydrogen. Don't use for any other metal. And the first 5 series, which for n is equal to, for example, 2, we have seen that was for Balmer. So this is true for Balmer. For n is equal to 1, it became for Lyman. For 3 became Paschen, and for 4 it becomes Brackett, and 5 become Pickford, because these are the people who found this. The target is 1, that is, they are coming to first orbital, they call it Lyman. If it is second orbital, they call it Balmer. Third orbital, they call it Paschen. We'll see this in the next slide actually. And again, please note, this is also from the experimental data at that point of time. So we'll see overview of that. So the line spectra of hydrogen, we have something like this. This is the visible one, and this is Balmer. Then we have Paschen, bracket P1, Lyman. They are not visible. Only Balmer is the visible one. And we see the way it works is, if n is equal to 1, that means my target is 1. It is jumping from any n is equal to infinity, 6, 7, 5. It is coming to 1. That series is called Lyman series, and there is generally ultraviolet, right? N is equal to 1 is ultraviolet. If it is coming to n is equal to 2, it is visible, actually visible light, and it can come from any place, right? It will be different colors. It can come from any place. If it is coming to n is equal to 3 from any higher orbitals, it is called Paschen. This is infrared. If it is coming to n is equal to 4, it is also infrared. It is coming to n is equal to 5, that's also infrared. That's how we saw. Here also we see, if you want a clearer view, if it is coming to n is equal to 1 from any place, it is Lyman. If it is coming to n is equal to 2 from any higher orbit, it is Balmer. If it's coming to n is equal to 3 from any orbital, it is Paschen. It's coming from n to n is equal to 4 from any higher orbital, is bracket. It's coming to n is equal to 5 from any higher orbital, is P1 series. That's how they have named the series. And this series are based on they are all of the people who found this series actually.
Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.